Hey geologists! So one of the things that happens in geology a lot is asking the question, how did that happen? So looking at the order of events, trying to figure out which layer came down first, which one came down next, when did faulting happen, when was some erosion that happened, those sorts of questions. So in this little video, we're going to look at the whole idea of relative dating and try to back it up, looking at which layer formed first, second, third, and so on and so forth. So how did that happen? So the first idea that geologists may look at is the principle that the oldest is usually on the bottom. So the principle of original horizontality and superposition. So horizontality means that the layers are laid down horizontally. Okay, so think about a layered cake. So you have the first layer, you put the frosting down, the next layer, and so on and so forth. So same idea in that the oldest is typically on the bottom and the youngest layer is usually or typically on the top. Now it doesn't always happen that way. So we have to look at the big ideas first and then try to piece together the puzzle. Okay? But the oldest is typically on the bottom and layers are put down horizontally. Now, here is a graphic that shows some of the order, how things could form. So in the first picture, I start out with my beach. So you can imagine a sandy beach there. And then over time, that sand may compact and turn into a sedimentary rock. So the second picture shows that dotted layer, and that's just a key to show that that would be a sedimentary rock that would form a sandstone. And you can see over time, thousands of years, millions of years, there may be an ocean that is laid on top of that sedimentary rock. Okay? And then that ocean may have fossils that form, so dead sea animals, and they turn to a different type of rock eventually. And so on top of that sandstone, I now have in my third picture a layer of limestone. So that brick-looking layer would be limestone. Over time, then, a swamp may form over top of the limestone. And then the creatures in that swamp may turn into a new rock called shale. But basically, everything is building up on top of each other. Now, on that last picture, the fourth picture, you can see that the sandstone is still there. It didn't go anywhere. It didn't disappear. But now it's down at the bottom layer, so things build upward. Okay? But again, they're laid down flat originally, all right? And the oldest would be on the bottom. Okay. Now in the next pictures here, we're looking at erosion. So if we have this wonderful layer of sandstone on the top, the wind and the rain and water may start to break that rock down. Okay. Now the important thing to know is that rock, again, didn't disappear. It was just the sediments were transported or moved elsewhere. Okay. And we show that on our image here as a little, wavy line at the top, that just some of those layers have been broken down. Now that sediment is still there somewhere. It's just moved to a different location. Okay. Some of the forces that may occur underneath the surface then are translated up to the crust. So we could have what's called a fault. And a fault occurs when you have a part of the plate breaks and some of it either moves up or down or sideways. And so I have this solid line to show this in our rock layer. Now an idea to look at here, an important idea, is that this doesn't have to happen on a plate boundary. Okay? It can happen in the middle of a plate. There are weak spots then throughout the crust. So again, you have underneath the crust, you have the mantle, and the mantle has some convection currents that are moving up and down. And so it could cause a weak spot in the crust, okay? So eventually, stress starts building up in places, again, not just in boundaries. And when that stress is released, boom, we have an earthquake, okay? The land may visibly change then in this case, and so we call that deformation, or the land may deform in some way, okay? So in my picture I showed a fault, and part of the crust then is lifted upward on there, okay? In this picture it's the same idea, only it almost looks like in this one that a part was actually pushed downward on here. So it depends on the type of fault that you have. So some of the rock may be pushed up, may be pushed down. It depends on the fault itself. Okay, And this, again, does not have to be on a plate boundary. It can happen in weak spots in the crust, too. Okay? When we go back to another form of an erosion, maybe glaciers. Okay? And so we have had different periods of time throughout Earth's history where a big chunk of ice, basically, moves across the landscape. And when it does that, it can flatten out the surface. So in this picture, you can see a giant glacier that's moving across the landscape, and some of the rock, then again, it doesn't disappear, is being transported elsewhere. It's eroding, okay? So sometimes I can leave a very flat surface on there. So the Earth has been experiencing glaciers then throughout the history, several glaciers. They either come and then they retract depending on the global temperatures. Back in 2001, this is a picture of the Rhone Glacier in Antarctica. And so you can see this massive chunk of ice, basically, that is going across the landscape here. And so it acts to kind of flatten out the surface as well. Okay. Now, another type of ways to change the landscape could be from an igneous rock. Okay. And we've talked about how intrusive igneous rocks are rocks that cool on the inside of the Earth. So the magma basically breaks through the surface or through the crust, and then it starts moving upward. And as it cools, you can get a new igneous rock that's in between the layers. Now, it may or may not break through the surface, but an idea here is that it's not necessarily a volcano just because you have an igneous intrusion in here. Okay? So in the picture, it's shown as that dashed kind of rock, so that could be granite, would be an example of an igneous intrusion that way. Okay? Here are some examples that we could see in nature. So you can see that I had my normal rock layer, and then it was broken apart. So I had the igneous rock kind of cross-cut through that rock. Okay? Here's another example in the Grand Canyon. So you can see I have a layer of shale right there, and then that igneous rock just kind of went through that shale. Okay. Now, as that igneous rock is moving through, it could heat up and increase the pressure of the surrounding rock. And when it does that, you do have the chance of a new rock forming. So you could have a metamorphic rock form. So for instance, in this picture, I have my igneous rock that's starting to go through my sandstone layer and also my limestone. So there is the potential that that rock could change. And again, it would just be kind of that area that's heated up with the increased pressure. So one example of an igneous rock changing the surrounding rocks could be this contact metamorphism of limestone. And then the limestone could change into marble. All right, so you could have a new rock. That's kind of cool to look at as well. So that's what the limestone changing to marble would be an example of contact metamorphism. So all of those processes come together to form this beautiful landscape that we have. And again, geologists really then like to see they're discovering what's underneath the surface, and that could help builders. It could help locate maybe oil or other natural resources. It could identify possible chances of erosion, of where things could actually erode, maybe even where groundwater is formed. So there is, or found, not formed. So there's lots of different potentials to figure out what is underneath.